Okay, it's 12:40, so let's get started. So the first question is linear algebra meets optimization, and we're given, can everyone hear me? Okay. It's just for the recording. I'm just going to speak like this. If you need me to speak louder, tell me. So in the first problem, we have a white matrix A. And we're asked to solve this ridge regression least squares problem. And we're going to solve it by calculating the gradient and then setting it to 0 because it's differentiable and it's convex. So we directly calculate the gradient of this. And set it to 0, and then we'll get the solution that we're pretty familiar with. Okay? And in part B, we're going to rewrite this problem into kind of a constraint optimization problem. And the problem is telling us to use Lagrangian and let the dual variable for this constraint be nu. And let's write out the dual function first, which is okay, you just dualize the equality constraint up to the objective function. Question?
Is this uploaded to your session?
We are actively uploading it right now. Sorry, it'll be up in a minute or two.
Thank you.
10 seconds.
Okay.
Okay.
So, right, we had this problem. We had this regularized least square, and then we introduced a variable called z, such that z is equal to ax minus b, and then we optimize with respect to z and x. Like this is kind of a dummy variable, but it will be clear later on. But and then you dualize the constraint, the equality constraint, up to the objective function. So you get this expression. Up to this part, it's okay, right? Okay, and we're gonna minimize over x and z. And let's just minimize over x first. So we do the same thing because it's a convex function, like convex, and then it's affine. And so we can set the gradient to 0 and then find the optimal point for x. So this is for the optimal x, and then we do the same thing for z. Okay, so we have x star and z star, and then the problem is asking us to solve the dual problem to get nu. So the dual problem is set up like this. And we plug in x and z into G to get the following, which is so there was a little bit of simplification, but the end result is this. And then we want to maximize nu to get the optimal nu. And if we observe again that it's a concave objective function. So we find the gradient and then set it to 0, so we find optimal nu. Nu is equal to okay, there was a bit of simplification, right, okay. And so the problem is asking us to get x and z without nu being in the expression. So we plug in what x is. X is going to be this, and we had we had z. Z was set to ax ax minus b, and so we write that. This, right? So we have this expression, and the interesting thing is that we had z as that expression as well, where z star is equal to minus 1/2 nu. And if we write that out as well, it's going to be and then we're going to later on see that these two are actually the same thing. This is what part C is trying to prove. Okay. So part C is asking us to show this. So this is called the push-through identity. You basically can push this through, and then this will be squeezed out. That's how I remember it, at least. Or it can be derived from Woodbury identity. But here we're going to prove this by using the SVD of A. And let's say A has the full SVD as follows, where U is okay, because we have a wide matrix. U is going to be full rank, and V is going to have at most rank M. And we're going to just plug this thing in to the left-hand side and also the right-hand side and see if they are actually the same. Okay? Let's do the right-hand side first. It was stated in the problem in the first part. It said that it was 4-row rank. So the right-hand side is A transpose A transpose plus I, lambda I, and then inverse. Let's just ignore the B for now because they're irrelevant. As long as this part is the same as this part, it's going to be equivalent. So we plug the SVD in. We're going to have and then we can manipulate this. So we have sigma transpose here. And if we let U transpose be I, the identity, then we can pull the U and U transpose out so that we get this thing. Okay.
Wait, sorry, could you explain how you did that?
Right. If we let this be U transpose, and they're going to cancel each other out, right? This is sigma transpose. And then U transpose, they're like on the outside. Okay, is that cool? And then we expand this thing. We get this because U and U transpose and U are gonna cancel each other out, and then we're left with, yep.
How do you know that V transpose V is the identity matrix if, like, isn't there the thing where if it's not like full rank, you can't? It's like the identity matrix isn't full.
The thing is that V in our case, oh, sorry. Oh, this is a typo, sorry. This should be n by n. Sorry, it's a full SVD.
Okay.
Right, so it's going to be orthonormal, an orthonormal matrix. V is going to be an orthonormal matrix.
Okay.
Right. Okay. And, right, so we have this expression. And then we're going to expand the left-hand side as well. And since we're running a bit late, I will simplify. I will ignore skip through all the steps, but up to the part where we have something similar to this. The manipulation is basically the same, huh?
How did you switch the sides on the left-hand side? You A.
Okay, this is the right-hand side. This is the left-hand side. Wait, did I copy it wrong? Right. Okay, and so you do the same thing. You plug in the SVD. Okay, and then you do this same manipulation. You plug, you let I be VV transpose, and then you pull the thing out so that you get to a very similar expression. It's just that it's going to be this thing. They're very similar. And what we want to do is to prove that they're equivalent, right? So as long as this part and this part, they're the same, then we can conclude that they're the same thing.
Why?
Because these two parts are the only difference between these two expressions, right? This is a U. Okay. Okay, and I'm going to let this sigma be sigma m and then 0. Okay? So sigma transpose is going to be a tall one. Okay, and let's calculate this thing. Okay? Because we had sigma to be this thing. Sigma transpose is going to be like this part. Okay? And then we have and for this part, we have okay, so as long as we prove these two are the same, then these two are the same, then these two are the same, then these two are the same. Okay? Question?
What was the point of going through all that?
Going through all this?
No, just like the block matrices.
This?
Yeah.
Because
Isn't the term on the right the same thing where you have the SM? One of them, the sigma m is on the left, and on the other one, the sigma m is on the right.
yeah, but you cannot.
This is what we have before.
So at least for me, it's not as intuitive to just look at, because, okay, so what you'll figure out is that this is diagonal and this is diagonal. And this is not diagonal because this shape is just wrong. It's a rectangular instead of a square one. So what we want to do here is we can say this is diagonal of sigma I and sigma I squared plus lambda. And this is the same. But you cannot really say that for this one.
Because this is sigma m versus sigma, right?
What?
Like that's the difference between them, right? The sigma m versus sigma.
Where's sigma? What difference?
In that side, in that one is sigma.
Yeah.
And in this one is sigma.
Yeah, because we made the sigma m to be square.
Okay, that makes sense.
Right. Okay, so these two are the same thing. Okay, all this is just to prove that these two expressions are actually the same. So you can push this through and then do some manipulation, and then you'll find out that they're the same. Okay? Okay, that was a very long problem, but yeah. Question?
Question about B. How were you able to find that the Lagrangian is convex and the dual is concave? Like, are there
This is like,
on the example?
huh? You can just say that concave, because it's minus, and then this is convex, right?
Oh, minus convex.
And then this is affine. So you can just say that. I think that's true. Maybe we can take it offline.
Yeah. Yeah, we need to get going with this next one. Where's the chalk? Okay, perfect. All right, cool. So we can start on problem 2 now, which is vector calculus. So 2, look at subpart A. So in this subpart, we want to compute the gradient and Hessian of this function f of x, which is given as f of x equals 1 minus a transpose x, whole thing squared. So we want to compute the gradient first. So gradient f of x. And there's a couple different ways to do this. I'll show you guys how to do it using the chain rule. So we can just work through term by term. So first, 1 is a constant, so we can ignore it. Then we can bring down the minus sign. And then we'll do the chain rule in this expression. So remember, the derivative and the gradient are different things. They're transposes of each other. And the chain rule works differently for these two things. So with the derivative, you put the outermost term on the left, and innermost terms go towards the right. But with the gradient, it's the opposite. So with the gradient, we put the innermost gradient on the left, and then the outermost on the right side for the gradient. So we'll take the inner gradient. So gradient of a transpose x is just a. And then we'll multiply by the gradient of the outer function, which is the squaring function. So we'll use the power rule to bring down 2 times a transpose x. So that is our gradient. And I can rewrite this a little bit nicer as negative 2 a transpose times x. So next, we want to compute the Hessian of f. And we know the Hessian is just the derivative of the gradient. So this is going to be derivative of negative 2 a transpose x. So all this is a matrix times x. So we can treat this whole negative 2 a transpose as a single matrix. Right? A transpose is going to be an n by n matrix, and the negative 2 is just a constant. And the derivative of a matrix times x is just that matrix. So this just equals negative 2 a transpose. So that's part A. Any questions on this? Yes? No. Because so if you think about it in terms of the channel for the derivative, with the derivative, we would put the derivative on the right, which is the transpose of the gradient, and then transpose that whole thing. So you'd end up putting the transpose of the gradient on the left, which is just the original gradient going on the left-hand side. So I think this is, I did it this way just to show you guys that you can do the chain rule towards the left for the gradient, which is a nice way to speed up your computations. But if you want to do it just as transpose the whole thing, take the derivative, transpose it back, and just use the same chain rule, that's also an equally valid way. The transpose of the derivative is the gradient, exactly, yeah. Any other questions? Okay, perfect. All right, we can move on to part B of this. So in part B, we have a different function now. So now we have f of x equals the sum, where I ranges from 1 to m, of the logarithm of b sub I minus a sub I transpose times x. So we're going to use similar techniques to take the gradient of this. So first, I want to take the gradient of f of x. The first thing I'm going to do is apply linearity of the derivative to bring the gradient inside the summation. So I'll have this sum, and then I have the gradient here inside. And then next, I'm going to use chain rule again, just like we did previously. So I'll bring down the sum, and then we'll use chain rule. So again, for gradient, you take the inner derivative, put it on the left, or inner gradient and put it on the left. So the gradient of this inner function is negative ai. That's the gradient of this. And then the gradient of the outer function, just the logarithm function, is just 1 over the item inside. So 1 over bi minus ai transpose x. And then we can write this out a little bit nicer as the negative sum I ranging from 1 to m of ai over bi minus ai transpose x. You mean here? Because we're taking the gradient of the inside. The gradient is always a column vector.
Oh, sorry.
A matrix optimization problem, right? Although it's an optimization problem, but it's a question asking about convexity. So we have this we have this optimization problem set up, and the first subpart is asking if the objective function is convex. And so there are a lot of ways to do this. We can first use the first principle, which is just the Jensen's inequality, see if it satisfies. And OK. Let's do that. You have x and y. If you grab 2 points from the from R n by n and see if the convex combination of these 2 points are going to be smaller than the Jensen's inequality. Let me just write it out. So the convex combination of these 2 points, is this going to be smaller than or equal to their respective values. So instead of proving the inequality, I'm just going to subtract one from another and see if this is going to be smaller than 0. If that's true, then this inequality holds. And if you recall what Frobenius norm is, it's going to be this thing. So this thing, and then if we simplify this, very quick simplification. I mean, there are a lot of steps in between, but you can refer to the solution after this. What it's going to simplify to is this expression, and then we'll realize that this and this, they're the same, and also they're strictly non-negative. Okay, and since we had theta to be within 0 and 1, this is going to be smaller than or equal to 0. And so what this means is that Jensen's inequality will satisfy. Okay? Right. And you can also do it by saying, okay, the Frobenius norm is convex, and then this square operation is also convex. So no, it's not convex. It's strictly increasing. So it's going to be a convex function. Okay. And well, yeah.
On the final, can we use that proof that all vector and matrix norms are convex?
I think it depends. If it is asking you to prove the norm itself is convex, then you might not be able to use that.
Like for this problem?
For this problem, yeah, I think you can use that.
Okay.
Yep. What did you say the other method was? The other method is, okay. Yeah. So this is method 1. Method 2. Okay, you can say okay, this is convex, and z squared on positive non-negative domain is going to be strictly increasing, so it's going to be convex.
Why are we allowed to?
Because this is going to be x.
Oh, because the inside element.
Right. Okay. Part B is asking us if the constraint set is convex. And the constraint set looks like this. This is the constraint set. Part B is asking if S is going to be convex. And so if we just take two points, let's say X is in S. then it means that sigma min of x is going to be bigger than 2. And what about sigma min negative x? It's also going to be bigger than 2 because the singular values, they're invariant to like multiplying by negative sign. And x minus x is going to be 0. And the sigma min of x minus x is going to be 0. So the convex combination of these two, which is, for example, x minus x, this is not in the constraint set. So the constraint set is not convex. Oh, yeah, OK.
Sorry. I was just like. Okay, thank you. Sorry.
Yeah.
Can you explain again why sigma min of negative x is still 0?
Because how do you explain this?
It's the eigenvalue to x, xt, right? And negative negative xt is the same as x, xt.
Right. Yeah. You can do that. You can, because calculating the singular value is like using x transpose x or xx transpose, and then you take a script. Yeah. Right.
Okay, so the next problem is on descent methods, number 4. So here we're just considering the least squares problem, which is minimizing 1/2 times the norm of ax minus b squared. And we're given some numbers for a and b. So a is 1, 2, 3, 4. And b is 4, 6. And in this problem, we're running gradient descent with initialization x0 equals 0, 0. And step size 1. So all we have to do in this problem is find the next iterate, which is x1. So given the gradient descent problem, the first step is, of course, to find the gradient of the objective function. So if that's f of x, then the gradient, as you've seen before, is just a transpose ax minus b. And then after we find the gradient, we just have to evaluate it at the given point, which is 0, 0. So evaluating the gradient as 0, we just get a transpose times 0 minus b, which is just negative a transpose b. So this is the gradient. And one thing that's nice about this question is in the hint, they actually provide you a bunch of calculations for you. So one of the given calculations is actually a transpose b itself. So this is just, in the hint, it says that a transpose b is equal to 22, 32. So this is just negative 22, negative 32. So now that we've found the gradient, all we have to do is apply gradient descent for one iteration. So x1 is equal to x0 minus, the step size is just 1, times the gradient at x0. So this just turns into the 0 vector minus 1 times negative 22, negative 32, which is just 22, 32. So this is x1. And any questions about this problem? Yeah.
Can you explain again why you were plugging in 0 to the gradient?
Yeah, so at every step of gradient descent, we have a current iterate, right? Where we start at x0, and we plug that into the gradient to find out, like that's the gradient we use basically. We use the gradient at the current iterate, and we subtract it from.
Oh, it's because x0 is the 0 vector.
Yeah, exactly. Yeah.
So you're plugging in.
Yeah. This is x0 basically, which happens to be the 0 vector in this case. Oh, sorry, x0. Any other questions? Okay, cool. Then we can do part B. So part B, we're looking at the exact same problem as before, with the exact same numbers as before, but now we're running Newton's method instead. So we have the same initialization as before, x0 equals 0, 0. And we want to figure out what is x1. So given how we did part A, you're probably tempted to just like use the equation for Newton's method. Like you would have to find like the inverse Hessian of this and then multiply by the gradient, blah, blah, blah. But does anyone know a faster way you could do this? Yeah.
It's quadratic, so Newton's method would converge more.
Exactly, yeah. So we want to find what happens after we run one step of Newton's method. It turns out that for quadratic objectives, Newton's method only needs one step to converge. So it's going to converge to the optimal value in just one step. So x1 is just equal to like x star, which is like the optimal value for this problem. And how do we find the optimal value for this problem? Well, it turns out that A here is invertible, and A inverse B is actually given in the hint. So the optimal value is just 0, and it's achieved at x star equals A inverse B, right? Like if we plug this into f of x, we'll just get 0. And obviously, we can't possibly get a negative value here. So 0 is the optimal value, and the x star is just A inverse B. So x1 is just equal to A inverse B. And they were nice enough to give us what A inverse B is in the hint. It's -2, 3. So this sort of underlines an important fact that you should know about Newton's method, which is that for QPs, or quadratic objectives, it's going to converge in just one step. Yeah, any questions about this? Yeah.
Can you explain why that's so really quick?
You can actually derive it from the equation. What Newton's method does conceptually is it locally approximates your function as a quadratic and then moves to the optimal value. So it's probably a good exercise for you to try plugging in the equation for Newton's method and seeing that it actually finds the optimum in one step. But conceptually, since it just approximates your function as quadratic and goes to the minimum as if it were a quadratic, it makes sense that it would take one step to converge. Yeah? Yeah, so it turns out that in this problem, like B is in the range of A, and A inverse B is provided in the question, so A is invertible and all. So, I mean, does it make sense why 0 is the optimal value of this, of minimizing this? Because this is a norm, right? Yeah, so since A inverse B is provided, that would be the optimal value here. We don't have to do the whole A transpose thing because A is already invertible, right? So, yeah. Any other questions? Yeah. Huh? Or what well, 0 will only be like the minimum value of this if B is in the range of A, right? Like otherwise, we would have to like do the whole like A transpose A inverse A transpose B thing. But it turns out here that A is already square and invertible. So we don't need this because the minimum value is just 0. And it's achieved at A inverse B. Any other questions? Yeah.
How would we know A is invertible?
I guess you don't know immediately, but looking at this, the columns aren't multiples of each other. And they also give the inverse. So, yeah. Yeah.
If A was an inverse, we would do this, right?
Then you would do this kind of thing. Yeah.
Wait, and that would be the answer even if B wasn't in the range of A, right?
Yeah. I mean, like in this case, it was, and A is invertible and all. So everything's in the range of A. So all we have to do is find A inverse B. Otherwise, you would just use this, yeah.
Okay.
This would be the answer.
And that would work even if A was not invertible. That would be the answer, whether or not B is in the range of A.
Yeah. If B is in the range of A, the answer is 0 is what I'm saying.
Oh, okay.
To the minimization of this.
Okay. But the minimizer itself would be that.
Minimizer is always this, yeah. Even in this case, it's this, but yeah.
Okay, sorry.
Yeah. No other questions? Okay, cool.
Okay, let's proceed with problem 5. So problem 5 tests a conceptual understanding of weak duality and strong duality. And for part A, it basically asks to find the primal minimum. So min over x such that of this thing such that x1 equals 0. Okay? And so, it gives you x1 is equal to 0. And so to compute this minimum, we basically can sort of plug this into here. And this basically gives us that we just need to minimize over x2 of 1/2 plus x2 squared. And by inspection, you can basically note that this minimum is achieved when x2 is equal to 0. So therefore, x2 star is equal to 0. And we know that x1 star is also equal to 0 because we have to have this. And that p star is equal to 1/2. Yeah, that's part A. Okay. Now part B is asking, let's see, does Slater's condition hold for part 2? Right. So Slater's condition basically, there's 2 criteria. You first need to have that the problem is convex. And I think we can observe that, if you look at the objective function, it's convex, right? Because you can take, it's twice differentiable. You can take the Hessian and observe the Hessian as PSD. So objective function is convex. The constraints are affine, so the feasible set is also convex. So we have that this is a convex problem. And and we also need a point that's in the relative interior of the domain, and which satisfies the affine constraints with feasibility and the non-affine convex constraints with strict feasibility. In this problem, we note that we only have one affine constraint. So we can basically pick, let's say, the point 0, 0. This is in the relative interior of the domain. And it satisfies that constraint. So using this point that we pick, and we're using the fact that this is a convex problem, we have that Slater's condition holds. And therefore, strong duality also holds for this problem. Okay, so that's part B. And what's part C? Let's see. Okay, yeah, find the dual problem. Yeah, and part C is basically a manual computation. Perhaps I'll move this board down. Okay, and so for part C, we again consider the general problem of x in R2, such of this thing. Such that x1 is equal to 0. Okay? And so to find the dual function, we do the standard procedure of first defining the Lagrangian. In this case, we define that Lagrangian with respect to x. And because we only have one affine constraint, we just need one dual variable. Let's call this, I believe this problem refers to as nu. Okay? So we plug this in first. And then we also add this equality constraint. So that's the Lagrangian. And then to define the dual function g of nu, this is basically defined as the min over x of the Lagrangian with respect to this fixed nu over here. And so to compute the minimum of this Lagrangian for this fixed value of nu and over any vector x, we can basically note that the Lagrangian is convex over vector x, because again, you can take the Hessian over x1 and x2, and we can observe that this is basically a convex function. And with that, we can basically use the main theorem and to conclude that any global minimizer of the Lagrangian will be obtained at any point, at any vector x, such that the gradient with respect to x of the Lagrangian, defined with this fixed vector nu and this vector x, is equal to 0. Let's compute the gradient real quick. So the gradient would be the first component of the gradient is the partial derivative of the Lagrangian with respect to x1. In that case, I believe that would be x1 plus 1, because this term right here. And we also add nu, for this term right here. And then for the second component, we're taking the partial derivative with respect to x2. So we would need 2x2. And so basically that tells us that any global minimizer will satisfy this thing is equal to 0 for our global minimizer x1 star, x2 star, if we assume that exists. And so by directly computing this, you can observe that we can therefore conclude that x star is equal to -1 minus nu, because this term has to equal 0. And we also conclude that x2 star also has to equal 0, because this term must equal 0. So what this tells us, using this fact, we can then conclude that this is basically the Lagrangian evaluated at that x star, which is -1 minus nu and 0, and our nu scalar. And then, basically you can plug this into here. And what does that give us? Let's see. It gives us 1/2 x1 plus 1 is nu, so nu squared, plus 0, plus nu times 0, which is 0. So, okay, I believe, okay, you need, so this would be 0 plus nu with respect to -1 minus nu. Okay, and then, this would be -1/2 nu squared minus nu. So this is our dual function. Therefore, we have this thing by basically evaluating the Lagrangian at our optimal points. And so that's the dual function. And then once we have this dual function, what's up?
Oh, I was wondering for x star, when you consider about the condition of x1 equal to 0?
The condition x1, okay, I mean, once we've converted this, once we've taken the Lagrangian, the constraints in the primal problem don't matter anymore, because they get converted to here. So basically, to compute this is an unconstrained problem with respect to x. Okay, so that's the dual function. And now with this, we can basically find the dual solution. D star is basically the maximization with respect to nu of g of lambda. Of g of nu. And we know that g of nu is concave, because the negation of g of nu is convex. So therefore, again, we can take the main theorem and basically deduce that the optimal of nu is where this gradient is equal to 0. And we note that the gradient of is basically negative nu minus 1. So therefore, nu star is equal to 1. It's equal to -1, -1. And so therefore, this thing right here is equal to g of 1, which is equal to g of -1, which is equal to 1/2.
Could we also just use the answer from part A?
Yeah, that also works, of course, to find the d star, right?
Yeah.
Yeah, this problem wants you to find the dual function, though.
Okay,
Yeah, but once you can, and then you can just, it also works, yeah.
What's the
Main theorem states that, okay, so if we have a convex problem that's differentiable, that has like differentiable constraints. Actually, do you need differential constraints? No, you don't need differential constraints. You just need a convex problem, so convex feasible set and a convex objective. And if your objective function is differentiable, then you can conclude that any point x such that this is equal to 0, any point such that the gradient evaluate at that point is 0 will automatically be a global minimizer. So if there's no inequality constraints, yeah, I mean, we've done that in part B, right? Yeah, I mean, part B we use Refine-Slaters because we have like an affine constraint. Yeah, so then we can directly conclude strong duality. Yeah.
How did you get -1?
Let's see, -1. Negative nu minus 1 equal to 0. Yeah, sorry. Let's make this clear. Yeah. In this case, no, because the relative interior of the domain is R2, because the domain itself is R2. So yeah, basically any point that's in the feasible set, because our feasible set is defined using affine constraints, will also be like a good point. Yeah.
Relative interior is just like anything that's like bounded.
Okay, I mean, the definition of the relative interior is not covered in this class. It's basically saying that if you take the affine whole of the set, and then in any point that's in the relative interior, any point is in the relative interior, if you can draw a ball around that point, such that any point that is in that ball, that is in the affine whole, is also in the set. Yeah. Yeah, okay. That's part. Okay. So yeah, that concludes problem 5. Okay. In that case, let's move on to problem 6, which again is like a conceptual understanding of like the whole duality formulation. Okay, do we have boards? Like this one?
Either of these.
Okay, yeah. Let's just use this one then. Okay, problem 6. Okay, so yeah, I mean part A. So we're given that we have this setup, P star is equal to the min with respect to x of this objective function such that we have these constraints. For all I in 1 to m. Okay? And part A is asking us if, okay, we know that all the functions fi are convex, and it's asking us what we can say about about the dual function. Okay? And we have the dual function is equal to this thing. For our Lagrange multiplier is lambda. And it's asking us whether this is convex, okay? I mean, so what do we know about lambda? I mean, what do you know about the Lagrangian with respect to lambda? So Lagrangian is basically, okay, so Lagrangian of this thing is equal to f naught of x plus the sum of lambda I fi of x. Okay? So that's the Lagrangian. So is the Lagrangian affine with respect to lambda? Yeah, so it's affine with respect to lambda. And so therefore it means that L is both convex and concave with respect to lambda. Okay? But what is G of lambda? This is a point-wise minimization of this collection of functions that are all affine with respect to lambda. So if it's a minimization of affine and therefore concave functions, the resulting minimization will also result in a concave function. So therefore, we can therefore directly conclude from this that G of lambda is concave. concave in lambda. Yeah, that's part A. Now for part B, it's asking you, now we don't know anything about the convexity of f of I, and it's still asking us if we can still conclude anything about g of lambda. Yeah? Is it jointly concave in lambda and nu? I mean, it's affine with respect to both lambda and nu.
Okay.
So if it's affine with respect to both lambda and nu, then I think if our x naught is fixed, then it would be jointly convex and jointly concave, I think.
Okay.
Yeah.
Wait, not necessarily jointly convex, right? Because pointwise minimum.
It's an affine function. Wait, are we talking about Lagrangian or the dual function?
Dual function.
Okay, yeah, the dual function, then it has to be concave. Yeah.
Okay.
Yeah. Okay, so yeah, I mean, okay, so this is a pointwise minimization of this set of functions. It takes the minimum out of the set of functions L of x naught lambda for all such that, yeah, x naught in R of something, okay? Let's just call it n. I think it's, okay, it's n, okay, fine, whatever. Yeah, so this is a pointwise minimization of this collection of functions with respect to lambda. Each of these functions are concave, so therefore we can take, therefore the pointwise minimization of this collection of functions that are concave in lambda will also be concave in lambda. Yeah. But note that, I guess an important thing to note is that if we take a minimization with respect to convex functions, then it won't be the case that this is concave. Yeah, so it has to be a minimization of concave functions is still concave, or a maximization of convex functions is still convex. Yeah, so that's, yeah. So that's the reasoning right here. Okay. Because this is lambda. I mean, this is Lagrangian, and it's concave with respect to each of these lambdas because these are constants with respect to lambda. So it's the sum of affine terms. Yeah, it's both convex and concave with respect to lambda. Yeah. Yeah. We can check both what? Okay, the Lagrangian is both convex and concave with respect to lambda. Yeah, we can only say that minimization of concave functions will be concave. It won't necessarily be convex because it's a minimization of concave functions. We need the maximization of convex functions to conclude convexity. Yeah. That's part A. And part B, you can note that what we did in part A did not rely on any of the convexity conditions on F, on each of the functions Fi. So therefore, we can directly copy-paste this conclusion into part B. Yeah. Okay, and then part C. Okay, so it's saying we have that each Fi are, F naught is linear and Fi is affine. And suppose that P star is equal to 0, which is strictly finite. And what's the strongest conclusion we can make about D star? Okay, I mean, I guess the conditions here that Fi are each affine is important, because then it means that we're only considering linear programs. And furthermore, we not only have that this is a linear program, we also have that this is a feasible linear program, because if it were not feasible, then P star would not be finite. So because this is a feasible linear program, we know that there exists a point in the feasible set, which would basically be the minimizer. And this point suffices in Slater's condition. So basically for part C, because we know that this is a convex problem, and we also have the existence of a feasible point that satisfies all the affine constraints with feasibility, then by refined Slaters, we can therefore conclude strong duality. And therefore, we have that P star is equal to D star, which is equal to 0. Yeah. Okay, does that make sense? because it's a linear program which has convex constraints and convex objective function. I mean, and more importantly, affine equality constraints. Yeah. Okay, that's part C. Part D. Okay, now suppose that P star is equal to 0, so we still have feasibility. And Fi is a convex function with respect to each of these. And furthermore, suppose that there exists a vector C such that for all I, Fi evaluated at C is equal to -3, which is strictly less than 0. I mean, this condition is basically setting up Slater's condition all over again. So we can again verify that this problem is convex. This point is in the relative interior of the domain, and it also satisfies all the convex constraints with strict feasibility. So again, by Slater's condition, we can therefore conclude that P star is equal to D star, which is equal to 0. Yeah. Okay, that's part D. Now what about part E? Part E says we still have feasibility. And now, actually, do we have feasibility? Let's see. Okay, we have feasibility. And Fi is a convex quadratic function of x for each of these, okay? And what is the strongest condition we can make about D star? Okay, so now we only know that our constraints are convex constraints, convex inequality constraints. So we can't use, so they basically, because these constraints are all convex, and we don't know anything about whether they are affine or not, then for Slater's condition to work, we basically have to have strict feasibility. So we need a point such that Fi of x naught is strictly less than 0 for all I. But is this directly given in the problem? It's not, right? It's not, so we can't use Slater's condition, and so therefore we can't make any conclusions about strong duality holding or not. Yeah? I mean, if it's a convex problem, we have to have that equality constraints are always affine. So for any convex problem, our equality constraints are affine functions.
Oh, really? Oh, okay.
Yeah. I mean, I don't see anything wrong with it right now. I think if you do that, that should be fine. But if the problem is written in the form of like if the problem has like equality constraints in them, then you would need them to be affine, I think. Okay, so let's see. So we have yeah, that seems fine with me. But yeah, I mean, for the purpose of Slater's condition, we need the equality constraints to be affine. Yeah. Yeah?
Why do I want
Fi to be convex in quadratic programs? I mean, for part E, right? I mean, in part E, they're given to be convex quadratics. I think for convex quadratics, having the convexity condition lets you conclude that the feasible set is convex, I think. Yeah, I think if you don't have that they're convex, let's see. If you don't have that they're, okay, yeah, I think the convexity condition lets you conclude the convexity of the feasible set. Yeah. Yeah, I mean, that's an edge case in definition of convexity. I think by default, we assume it's convex because there doesn't exist a feasible set that's non-empty to begin with.
Okay.
Yeah. Yeah. So then basically we can only conclude, yeah.
And this is like always true for,
Yeah, this is always true.
like, even if no function is convex, like, so.
Yeah, it always holds by the minimax inequality.
Okay.
Yeah.
Thank you.
Yeah.
So for part E, which option should we choose? We just choose none of above, right?
Yeah, none of the above.
Okay.
Yeah. Yeah, that's it for part number 6. Yeah.
All right, guys.